I have the pleasure of introducing Cricket Lou here from Infoblox to give a presentation about DNS. Cricket has been, I guess, one of the leaders and foremost experts in DNS. He has written several books, one of which I grew up on, learning DNS and Bind by O'Reilly. And he's currently one of the fellows at Infoblox. So I give you Cricket.
All right. Thanks, Sean. Thank you. Can you hear me okay? Yeah, okay, good. So let's talk a little bit about DNS, because that's really all I know enough about to talk about it in any kind of confidence. So I'll tell you first just a little bit about myself. I started doing DNS way back in 1988. That's before most of you were born, I would imagine. And it wasn't something that I was particularly interested in. I actually started working for HP after I graduated from college, working for a department that did office automation strategy, determining, for example, whether we would use Microsoft Word or ME Pro, or whether we would use Lotus 123 or Excel or what have you, and completely fell into DNS. We were also the department that ran the HP Internet, which back then was the largest private TCP/IP-based network in the world. And one morning, I got up at my house in San Francisco, and I got a call from the manager of one of the guys I carpooled with. And he said, hey, John has had a family emergency, and he was registered to go to a class in downtown San Francisco, and it's way too late for us to get our money back, but you could go in his place. And I said, oh, well, does that mean I don't have to go to work? He said, yeah, you can just go to the class. And I said, all right, sounds good to me. And then I said, oh, well, what's the class about? And he said, it's about DNS. I said, all right, I don't know anything about that, but it sounds interesting. And the class was taught by Paul Makapetris, who, if you haven't heard of him, is actually the father of DNS, the guy who came up with all the original concepts, who wrote the first set of RFCs and the second set of RFCs, wrote one of the first implementations of a DNS server ever. For an operating system called TOPS 20 that ran on DEC Vaxxon. So I went back and started messing around with name servers, and I've been doing it ever since. So that was where I cut my teeth, running DNS for HP and running the HP.com zone, which was a big zone, 135 subzones or something like that. And I joined Infoblox about 14 years ago and have been working for them ever since. So I'm now a senior fellow, which means that I don't have to come in first thing in the morning, and I can leave a little earlier. If you want to get a hold of me, you're welcome to. My email address is up there at the top. I do have a Twitter account where I send out things that are DNS related, and I have a blog. And I should have mentioned this as well. My buddy, an old friend of mine, Matt Larson, and I have a podcast. And if you're really, really interested in DNS or just can't sleep, you can listen to that. It's the Ask Mr. DNS podcast. It's available on the iTunes store. But let's start talking a little bit about DNS and how DNS works. The domain name system, as probably most of you know, is the Internet's naming system. In fact, it is the standard naming system for any TCP/IP-based network. It's a distributed database system. It's client-server based. We'll talk about the clients and the servers. The clients are typically called resolvers, and the servers are called either name servers or DNS servers. And its primary role is mapping domain names, which are those funny dotted names that you see in URLs, for example, or on the right-hand side of an @ sign and an email address, for mapping those to IP addresses or other types of data. So we'll start with a brief history of the domain name system and how it came to be. Now, when the ARPANET began, the ARPANET had a single monolithic text file that contained named IP address mappings for every computer on the network. It was called hosts.txt. Everything on the internet, the precursor to the internet, the ARPANET, was in this thing. And it was maintained by a single organization up in Menlo Park called SRI. It was their Network Information Center, or the NIC. This is what it looked like. Pretty simple format. And actually pretty similar to host.txt on like a Windows machine, or the etc hosts file on Linux if you're used to that. In the first column here, you have something that says host. That just describes what it is that we're talking about on this line. There's also gateway entries and network entries. There's a colon delimiter, then the IP address of the host, followed by possibly a list of other IP addresses separated by a comma, a colon, followed by the canonical or official name of that host, which is just a text string, possibly followed by one or more aliases separated by colons, and then another colon, the hardware architecture of the host, another colon, the operating system that it runs, another colon, and then a comma-separated list of services that are supported by that host. So that's what it looked like. Great big file, as you might imagine, because there was one line in it for every host connected to the ARPANET. Now, as the ARPANET grew and became the internet, and we had more and more and more computers connecting to the ARPANET, this became a pretty big file. Can you imagine any problems that we'd have with this file? What kinds of issues would we have with all of these records in one file? It became large, right? It actually took up a pretty substantial amount of space. This is an era where a 20 megabyte hard drive was actually fairly large. Searching, yeah. So one of the things that's a little subtle here is that the entries in here are not in any particular order. Right, so if you're looking to do a named IP address mapping, you just have to start at the beginning of the file and do a sequential search for the name that you're looking for and return the IP address. Right, so that's an order n operation, n being the size of the file. At HP, where we were eventually decommissioning our host table at the end was about 75,000 lines long, just internal hosts. The slower computers of the day, which were based on Motorola's 68,000 microprocessors, they would time out before they got to the end of the file. So system administrators back then took to actually sorting the entries in the file. So they would take the hosts that they would access the most frequently and sort them to the beginning of the file. That is incredibly dull. I mean, I can't imagine a more boring task to do. That's right. Really, really old school. So any other problems that you could see with something like this? Yeah. That's right. That's right. So there's only one organization, SRI NIC, right, that actually updates this thing. And they only do 2 updates of the file every week, on Tuesday and Thursday. And you have to email entries to them. You have to say, hey, I have a new host. And if you actually send that to them, say, on Friday, no one's going to be able to access that host until the following Tuesday when the new version of the host table rolls out. Another thing is that if you look at the names of the hosts, it's a flat string. The name is just some sequence of characters. And so there was the possibility of having naming collisions. For example, once all of the popular names like Frodo and Bilbo and things like that were gone, nobody could have them. So you had to go search the file before you gave a new computer a name. You had to search the file to determine if your name wasn't already taken. It's like getting a license plate, a personalized license plate here in California. So, consistency and latency, those were a big problem. Traffic and load on SRI NIC, they were actually using most of the bandwidth provided by one of the backbone links on the ARPANET just for transferring the file around, which was 56 kilobits per second, which doesn't sound like much now, but in those days that was a lot. Naming collisions and searching the file took a long time. So we knew that this was an issue, and in the early 80s we commissioned a study into a successor to the host.txt file. And it would provide local administration, so you'd be able to take care of the data that you wanted to publish locally and yet make that available globally. And it would also use a hierarchical namespace, so we could do away with this whole naming collisions problem. We'd had lots of experience with hierarchical namespaces. File systems, for example, used hierarchical namespaces. So this is a timeline of sort of when this was going on. The original RFCs, 882 and 883, that described DNS were published way back in 1983, and we did the transition from host.txt on the ARPANET to DNS between 83 and 1984. In 84, Bind 4, which is the sort of preeminent, it was the first open source implementation of a DNS server, was released. The modern quartet of RFCs that describe DNS, which are sort of like the Old Testament, if you will, of DNS, 1032 through 1035, were published in 1987. Microsoft came out with their Microsoft DNS server back in 1993, and then we had various versions of Bind that came out later on. The current version of Bind, which is a version of Bind 9, traces its roots back to something that was released 16 years ago in 2000, believe it or not. So let's talk a little bit about how this stuff works. So we had this thing. Oh, that's interesting. I didn't think this was the first part. So we have this thing, this inverted tree, which is the structure of names in DNS. Have you guys seen this before? Have you seen a diagram like this before? So you'd see inverted trees, for example, if you were looking at a diagram of a file system or something like that. But this inverted tree is a diagram of the structure of names in DNS, right? Let me see. I think we're a little bit out of order. Let me just take a quick look here. I'm not sure how we got out of order so quickly. Well, I guess we're okay. All right, I'm going to have to freewheel it a little bit. Okay, so the namespace. Within the namespace, every connection point here is called a node. Every node has a label associated with it, and the labels range from 0 length to 63 bytes in length. Right? They're typically textual labels. There are some restrictions on what the format of the label can be. Each label can have any number of labels below it. Up at the top, we have the root. The root has a special label. It's a 0 length label. Only the root can have a 0 length label. It's usually written as a pair of double quotes because it's difficult, obviously, to write a 0 length label. And then we divide this overall namespace up into what we call domains. A domain, if you're thinking in terms of graph theory, is a subtree of the namespace. So for example, we have a domain that starts here at this node, which is called the com node, and extends down to the bottom of the tree. So if you think about this as a mobile hanging from a ceiling, it's what you'd get if you clipped the link above the node up at the apex, right? And everything that hangs from there, that's the domain. And so the domain contains all of these various nodes. The way that you read the name of a particular node, called the domain name of the node, is the list of labels from that node up to the root. So for example, this is the com node, or sometimes you'll even see com dot, and then that 0 length label. You use a dot as the separator between those labels. Okay? So subdomains. A subdomain is just a domain that's within another domain. For example, here we've got the com domain. The com domain has subdomains that are rooted at these nodes that are below the com node. So for example, this is maybe infoblox.com, or it could be oracle.com, or it could be any number of other things. And again, that's that subtree rooted at that node, and it extends down to the bottom of the tree. So organizations out there on the internet typically manage domains, right? So there's an organization called ICANN, the Internet Corporation for Assigned Names and Numbers. And they run the root domain, right? The very, very top of the entire namespace. VeriSign, a company that you may be familiar with because they're actually headquartered up in Mountain View, they control the com domain under special license from the US Department of Commerce. Actually, though, that's kind of a fib because the domain, of course, is everything that extends from that particular node down to the bottom of the namespace. So the root domain really contains everything, right? Every single node in the namespace hangs from the root node. So there has to be some sort of a different construct, right? ICANN can't control everything. So we have this concept within DNS which is called delegation. Delegation allows you, as the administrator of, say, the root or com, to give away, if you will, management of a particular subdomain. So the guys at ICANN give away management of the com domain to the folks at VeriSign, and they give away management of the edu domain to the folks at an organization called EDUCAUSE, and they give away the management of the UK domain to the folks at an organization which is based in the UK called Nominad. So now the parent and the child are different administrative containers. Right? The parent is administered at that point separately from the child. And at that point, they're broken not into domains, but actually into what we call zones. So a zone is a unit of administration. If you think of, say, the difference between the root domain and the root zone, the root domain is everything from the root all the way on down. And the root zone is only the root domain minus the things that are delegated away. Right? And almost everything under the root is delegated away to somebody else. So here's a diagram of this. Here's the root zone in this sort of, what would you say that is? Sort of a tangerine color, maybe. And then this red slash indicates delegation to the COM zone. Below the COM zone, we have delegation to some other subzone pictured here in green, another subzone pictured in blue, and so on. Now, the internet has grown up to have a namespace that looks a particular way. Initially, the internet had only 7 top-level domains, and they were called COM, which was used by commercial organizations, EDU, which is used for educational organizations, like University of California at Berkeley, which runs berkeley.edu, or San Jose State, which runs sjsu.edu, Gov, which was used by US governmental organizations like NASA or the FBI, places like that, INT, which is the international top-level domain, used by organizations like NATO. It's used by IATA, the International Air Transport Association, other places like that, the United Nations. MIL, which is used by the US military, such as the US Air Force. NET, which initially was restricted to networking organizations, but later opened up so that anybody could register within it. And then org, which was used initially for non-commercial organizations. So you had to be kind of a nonprofit or something like that to be an org initially, and later on it was opened up to just about anybody. Initially, there was also this transitional top-level domain, which is called ARPA. ARPA was created because folks were worried that when you moved a host out of the old host table and into DNS, people might not be able to guess what its domain name was. So, for example, we were talking about how the host table was distributed from this one organization, SRI-NIC, right? And they actually had a computer that did that distribution. It was called SRI-NIC. Well, SRI-NIC eventually became, in DNS terms, nic.ddn.mil. But unless you'd read something, you might not know that. So ARPA was a placeholder where they'd create an alias so that SRI-nic.arpa would be an alias to the new domain name, nic.ddn.mil. So you had an algorithmic way of figuring out where a host in the old host table had moved in DNS. All right, so later on, the namespace expanded. One of the big expansions was the ISO 3166 expansion. Basically, ISO 3166 is a standard document that reserves 2- and 3-letter country codes for every country in the world. And basically they said, all right, the internet is expanding. We're going to reserve top-level domains for every country in the world according to the 2-letter abbreviations in ISO 3166. So these are the ones that you see that end in .in for India, that end in .uk for the United Kingdom, actually for Great Britain, but that's another topic. So all of these were reserved in one fell swoop. Right. And the structure below that really depends entirely on the country. So some of them, for example, like Australia, have subdomains like edu.au, which is their version of the top-level edu. Other ones, like Germany's DE, they break directly into subdomains that are allocated to organizations. So Siemens is, for example, siemens.de. There's no siemens.com.de. So that top-level namespace has kept expanding. ICANN later allowed another tranche of expansion. They added really kind of a motley collection of top-level zones. Aero for the aerospace business. I don't know who uses that. Biz, which was intended to be kind of a competitor to COM and never really took off. This is co-op, not coop, which was for co-ops. Museum, travel, and things like that. A lot of things that didn't really take off. And then much more recently, in the last couple of years, ICANN basically said, all right, anybody who has enough money can come along, write us a check for about $185,000 to apply for their own top-level domain. And so this is this much more recent onslaught of new top-level domains. Sometimes they'll belong to a particular brand. For example, Canon, the Japanese company, has one. There are geographical ones, there's .tokyo and .rio and things like that. And there are others that are actually generic in which anybody can register. So there's adult and church and rocks and sucks and all kinds of stuff like that. Basically a big play by the Internet Corporation for assigned names and numbers to get as much money as they could out of folks using the internet. So let's talk a little bit about name servers and zones and authority. We've talked about the namespace. We talked about how delegation breaks domains up into zones. And now we'll talk specifically about how that relates to name servers, which are the server components of the domain name system. So as I said before, DNS is a client-server system. The servers are name servers or DNS servers, and the clients are called resolvers. And the resolvers send queries to name servers answer those queries. Right? Now, name servers load data in units of zones. Right? These are the administrative units in DNS, like we said. So, for example, here, one of the big zones is sjsu.edu. Right? Name servers don't have to load just one zone at a time. They can actually load thousands of zones or even tens of thousands of zones. But no one name server has the entire namespace. Every name server just has individual zones that comprise a relatively small proportion of the overall namespace. The namespace is so large now, for example, if you look at COM, there are something like 100+ million delegations under COM, which is why you can't get any domain names under COM that you really want. A name server that loads an entire zone is said to be authoritative for that zone. It can answer any question that it receives about the contents of the zone. What's www.sjsu.edu's IP address, right? Where do I deliver mail that is addressed to sjsu.edu? That sort of thing. So the entire system is actually a little more complicated than the traditional sort of client-server system because name servers have to also have the ability to navigate this fairly complex namespace. Right? As I said, any one name server only knows about some pieces of the overall namespace, some zones. It may be authoritative for thousands of zones, but it still doesn't know anything about all of the zones in the world. And as a consequence, these name servers have to have the intelligence to navigate through this namespace, find the name servers that are authoritative for the zones that contain the data that they're interested in, query them, and get the information back. So we'll talk a little bit about that in an upcoming section. First, though, we're going to talk about resolvers, the client side of DNS. This is the client half, right? These are not, generally speaking, separate pieces of software. They're not individual processes, for example, that run under Unix or Linux. Generally speaking, they're just part of the standard shared C library in an operating system. Sometimes on a more sophisticated, more modern operating system, they might be a slightly separate process that does a little bit of caching or something like that, but they're pretty dumb. They're pretty simple. Even a lot of simple internet devices have resolvers built into this. The Nest thermostat on my wall has a resolver built into it, for example. And what does this resolver do? Well, the resolver takes an application's request for data in DNS and translates it into a DNS query and then sends that DNS query to a name server and awaits a response. Now, it may have to retransmit that if it doesn't get a response within a certain amount of time. It may have to try a different name server if that name server doesn't respond. If it does get a response back, what it's going to do is it's going to tear apart the DNS message that contains the answer, and it's going to unmarshal that into a data structure and then pass it back to the application. So why do you think you need things like this? Why do you need resolvers? What's the use of something like this? I mean, you could write an application that sent a query directly to a name server. So what does a resolver buy you? Anybody? Well, it prevents all those application developers from having to understand how to deal with a name server, how to put together a legal DNS message, right? It prevents everybody from having to implement those retransmission algorithms over and over and over again. It gives you a convenient API for communicating with DNS, which is why we have these resolvers in the first place. Right? So here's how this all works together in a process called resolution. So this is the process where a resolver typically sends a query to a name server, and that name server goes out and navigates the namespace, and it communicates possibly with a number of other name servers authoritative for various zones, until it finds the name server that's authoritative for the zone that contains the answer that it's after. Right? So eventually it'll find its way down there, grab the answer, right, and return it to the resolver that asked. So here's a diagram of how that works. This is the namespace over here. I'm going to try to show how the communication among these little boxes corresponds to navigating that namespace. So we're going to start by having this resolver send a query to that name server. And it's going to look up something that's, say, www.infoblox.com's IP address. And this name server, if it has no other information, no more specific information, then it's going to go to one of the root name servers, that is one of the name servers authoritative for the root zone. So it's as though it's starting at the very, very top of the namespace. It says, I don't know, but I can get anywhere if I start from the top of the namespace and work my way down. And he's going to ask the root name server, hey, what's the IP address of www.infoblox.com? And the root name server responds and he says, well, I don't know what the IP address of www.infoblox.com is, but I can see that that domain name ends in com, and I know where the com name servers are, so I'll send you a referral to those com name servers. And then that name server is going to follow up on that. He's going to turn around, he's going to choose one of the com name servers to query, and he's going to ask it, hey, what's the IP address of www.infoblox.com? The com name server says, well, I don't know what the IP address of www.infoblox.com is, but I do know where the infoblox.com name servers are, right? So you're sort of moving that next step down the namespace. And I'm going to send you a referral there. So you work your way there. Now you've got a list of infoblox.com name servers to query. You choose one of them to query, right? And it responds, and it says, oh, I know the IP address of www.infoblox.com. It sends you the answer. The name server here passes that along to the resolver. The resolver passes it up probably to a web browser, and the web browser then tries to connect to that IP address. Right? So that's how the thing all works together. Now, the one name server here in the center, you'll notice, did a whole lot more work than the other name servers. These name servers could be relatively lazy. They could just say, I don't know, go talk to the com name servers. I don't know, go talk to the infoblox.com name servers. This one, for some reason, had to do all the heavy lifting of following up on those various referrals from other authoritative name servers. Now, why is that? Why is that? Well, the answer is recursion. Somebody has to take on that responsibility, or you can't navigate the namespace. So when a resolver sends a query to a name server, it sets a little flag in the query which says, I need recursion. I need you to do all of the work necessary to get the answer for me, because I don't have the intelligence to follow a referral myself. You can't tell me go talk to the root name servers because I can't do that. Right? So he sends this recursive query, and by accepting a recursive query, the name server in the middle of that diagram says, I'm going to do all of the work that's necessary to find an answer for you, and then I'm going to send that back. But when the name server sends other name servers queries, it sends non-recursive or iterative queries. The iterative query just says, tell me the best thing you already know. Don't send any other queries on my behalf, but if you're a root name server, just tell me the appropriate top-level zone name server to talk to. If you're a name server authoritative for a top-level zone, tell me the appropriate name servers for the second-level zone below that to talk to. Right. Now, these queries in responses are just DNS messages. DNS messages carry queries, responses, things called notifies, zone transfers, any number of different things. These are usually based on UDP, the user datagram protocol. You guys know about UDP? Yeah, connectionless, right? Lightweight, low overhead. And they all share this common format. They can have up to 5 different sections, a header section, a question section, sometimes an answer section, an authority section, and additional data section. So the header just indicates things like, is this a query or is this a response to a query? Indicates whether it's recursive or not recursive. And then the question section says, hey, this is the domain name that I'm interested in, and this is the type of data that I'm interested in. I'm interested in an IPv4 address. I'm interested in an IPv6 address. I'm interested in mail routing information. I'm interested in a text record or something like that. Right? The answer, authority, and additional data sections all carry the records that actually answer these things. So, for example, in that diagram that we saw of navigating through the namespace, working our way down to finding the IP address of www.infoblox.com, in the referrals that came from the COM name servers and that came from the root name servers, we would have found those in the authority section. We would have found within the authority section a list of what we call NS records that designate name servers for a particular zone in the namespace. When we got the IP address for www.infoblox.com, eventually that would have been, for example, in the answer section. So if you had to go through that whole process of working your way down from the root name servers every single time you had to resolve something, that would be fairly slow, right? It would also mean that the root name servers would be really, really, really busy. Now, there are a lot of root name servers out there on the internet. It looks kind of like there are 13, but in fact there are hundreds of them. But still, if every single time somebody wanted to look up a domain name, that search had to start at the root name servers, those things would be an enormous bottleneck. So one of the things that speeds this whole process up is caching. So if, for example, we're resolving www.infoblox.com like we did in that previous example, there's a lot of stuff that this name server here can cache after going through that. So for example, it's learned from the root name server that it communicated with the list of COM name servers, right? So we can cache that. It's learned from the COM name servers the list of infoblox.com name servers, so it can cache that. And the next time it has a query to process, it can look at all that cached data and see if any of it relates to the query that it's processing. Does any of it help speed up the resolution process? Say, for example, that you look up www.infoblox.com, again, the resolver sends another query to the name server, or a different resolver using the same name server sends the same query. At that point, the name server just responds. He just says, oh, here's the answer. I have it in cache. Right? Or, for example, what if you're looking up support.infoblox.com? Something has gone wrong with your Infoblox name server, and you want to contact support, so you're going to go to our support site. Well, then the resolver sends a query to the name server. The name server says, do I have an address for support.infoblox.com? No. Do I know where the name servers for infoblox.com are? Yeah, sure, I've got that information. So I can skip going to the root name servers, I can skip going to the COM name servers, I can go directly to the infoblox.com name servers, and get the answer, and send it back to the resolver. Right? HP.com, similar sort of thing. You say, hey, I've already got COM name servers, so I can go directly there. Get a referral to the HP.com name servers, ask them, get an answer back. So typically, after running for any reasonable length of time, a recursive name server like the one in the middle of the diagram here will have a fairly rich cache. It'll have all the root name servers, it'll have all the COM name servers, it'll have all the name servers for every top-level zone that you routinely communicate with. So obviously, caching presents kind of a problem. You can't cache something forever, right? If you do, you're never going to recognize when things change. For example, if you cache the IP address of www.infoblox.com and you do so forever, if we change the IP address that www.infoblox.com is supposed to point to, you'll never see it. So all of those records that we're handing back have to have something associated with them called time to live. And time to live is just a measure in seconds of how long you're allowed to cache that particular record. And it's set by the administrator of the zone that contains the record. So for example, you guys, somebody shy maybe, you're responsible for managing sjsu.edu. So if you have an address record in the sjsu.edu zone for www.sjsu.edu, then you get to determine what the time to live is, right? How long it can actually be cached. Now think about that in terms of pros and cons. Why would you want to have a long time to live? Yeah, if it's relatively static, and that would mean that people could cache that for a long time and they wouldn't have to come back to your authoritative name servers very frequently. And on the other hand, why would you want to have it very short? Yeah, what would induce you to have a really short time to live on data? More clients can connect? Update. Well, yeah, if you're updating it, if you're changing what it maps to frequently. For example, maybe you're doing some sort of load balancing. Maybe you've got multiple web servers that you have www.sjsu point to, and you want to move it around. You want to move the named IP address mapping around to point to the web server that actually has the lowest load at any particular instance. Something like that, right? So that might require a shorter time to live value. Yeah, exactly. If you know ahead of time, hey, I'm going to have to move, even if you have fairly static infrastructure, if you know that you're going to have to move your web server from one IP address to another, then in anticipation of the move, you might ratchet down the time to live value on your address. And then after the move, make sure that when you actually change over, you have a relatively short time to live. Then you can raise it back up to whatever a normal value would be. Right. All right. I think the last thing that we're going to talk about in the world of DNS is something that it's a little bit arcane, but it's I think a very cool mechanism, which is server selection. So most zones out there on the internet have more than one authoritative name server. The root zone looks like it has 13 name servers. Their names are A through m.root-servers.net. Even littleinfoblocks.com, we've got, 4 or 5 authoritative name servers. You guys probably have 6 or 7 name servers. So a lot of name servers. So that recursive name server that we saw in the middle of that diagram, it's almost always got a choice, right? And I kind of glossed over how it chose. I just said, well, it chooses one of the root name servers. It chooses one of the com name servers. How does it choose, though? We'd hope that it chose in kind of an intelligent way, right? Also, what happens if you send one of these UDP-based queries out to the internet and you don't get a response? It's UDP after all. Cosmic Ray can come down and flip one of the bits in the DNS query message and corrupt it. It can just get lost. You can have congestion. Any number of things can happen that can cause it to get lost. So you have to be able to handle that situation because it's UDP-based. You have to be able to retransmit the query. Now, server selection, what you do when you are faced between a choice of authoritative name servers to query, does vary depending on make and model of name server. So I'll describe the way that a bind name server does it. Other recursive name servers like Microsoft DNS servers do it in a slightly different way, but generally speaking, name servers are pretty intelligent. Bind name servers use a mechanism called round trip time to choose among a set of authoritative name servers. Basically, every time they have a choice among a set of name servers, they choose one initially at random, and they start this little internal stopwatch. And when they get a response back, they stop that little stopwatch and they say, okay, it took you about, say, 53 milliseconds to respond, so I'm going to record that as your round trip time. So after, say, the first 13 queries that they need to send to the root name servers, they will have chosen every one of the 13 root name servers at that point, and they'll have a round trip time for every one of them. And they'll know, generally speaking, which one is closer, which one is responding more quickly. Right? They don't really know things like, well, is it responding slowly because it's busy, or is it responding slowly because it's in Papua New Guinea, or whatever. They just know, well, it took that guy 253 milliseconds to respond, that guy took 51 milliseconds, so that's the guy I'm going to go to. Right? So it's a pretty straightforward mechanism. They also keep updating that value, that round trip time. So even after they've communicated with those first 13 root name servers or 13 com name servers or whatever, they keep updating the round trip time. So they'll choose to query the root name server that has the lowest round trip time, but they'll again sample its round trip time, and they'll calculate a weighted average then of its previous round trip time plus the new sample. I think that bind name servers now use like 70% of the old average plus 30% of the new sample. That becomes the new round trip time. If the name server doesn't respond at all, of course, you penalize it by giving it a much higher round trip time. Right? And then, because you don't want to starve a name server out, because you don't want a situation where, well, that name server was slow, and so I gave him a high round trip time, and then I never tried him again, you also decay the round trip times. So every time you do not choose a set of name servers, you decay their round trip times by multiplying them by, in Bind's case, about 0.98. So they gradually sort of creep down if you don't query them. They gradually creep down to where they're competitive again. You throw another query at them. Maybe they're a lot faster this time. If they're still slow, they jump back up to where they're not going to be queried as often. So there's also retransmission. Again, retransmission depends on the implementation. All name servers, however, all recursive name servers are able to send queries and wait, and then either retransmit to the same name server or try a different name server. And how they do that, unfortunately, entirely implementation dependent. So, and that brings us to authoritative, recursive, and caching name servers, which are just roles that name servers play. An authoritative name server is just one that is authoritative for one or more zones. That's it, right? Its primary role is advertising that data to the internet or to some network. Some of them do not even offer recursion. If you sent these name servers a recursive query, they'd say, not doing that for you, right? Go somewhere else. Right. Recursive name servers are those name servers like the ones we saw in the center of the diagram. These are the name servers that go off, they send multiple queries as necessary, they follow referrals from other name servers until they identify the name server is authoritative for the zone that contains the answer. They grab that data and they return it. So, any questions about DNS? That's your quick, like, what was it, 45-minute introduction to DNS. I will say that these slides are from some video training that I did for O'Reilly a couple of years ago. O'Reilly is, generally speaking, a book publisher, but they say that millennials like you folks like to learn in a different way and prefer video training. So I did a whole video series of these things. So if nothing else, your sitting here has given you maybe $50 worth of training. Yeah, Shai, go ahead.
When you talk about server selection, how does that going to work with Ncast?
Well, the key is that name servers actually don't realize that another name server is Anycast. So they select purely based on round trip time. So what they'd be testing in the case that one or more of the authoritative name servers were using an Anycast address, what they'd be testing is actually just the round trip time to the closest Anycast instance.
Really goes the routing handles that.
That's right.
And then the DNS server is really the customer of that.
That's right.
The network.
That's right. And in fact, of the 13 root name servers, man, they're all Anycast. All but one are massively Anycast. Some of them are 70 plus individual instances. Yeah?
You mentioned the name server will do the recursion thing. So is it like it will keep on calling from one server to another server until and unless it will get the reply? Something like that? It will just process the thing.
No, it doesn't broadcast. Name servers don't broadcast at all. They will only ever use unicast messages. So the recursive name server, for example, if it has to look up www.infoblox.com and it has the list of infoblox.com name servers, it chooses one of the infoblox.com name servers to query. If it's running bind, that's according to round trip time. It queries it and it waits for a response.
How does the recursion goes over here?
How does the recursion what?
How does the recursion goes over here? I don't understand the concept of recursion. Recursion is like it will keep on doing the same task, right? Unless something breaks. So
that's right, but that's what we showed in that diagram when you saw the recursive name server in the middle. It starts at the root name server, it sends a query, it gets a referral to the com name servers, it queries one of the com name servers, it gets a referral to the infoblox.com name servers. Right? It's using the same process over and over and over again, but gradually refining the list of name servers that it's querying and getting closer and closer to the answer, which is a little bit like the concept of recursion in software. Yeah?
when does it use TCP?
That's a really good question. So DNS can use TCP. Typically what happens is that when a name server queries another name server and the other name server is trying to answer the querying name server but cannot fit the entire answer into a UDP-based DNS message, it'll signal that. It'll set a bit in the DNS message header, which is called truncated. It's the TC bit. And it says, I'm going to put everything I can into this message, but I'm going to set that. And the recursive name server then can choose. It can say, well, I got enough information here, I got what I needed, or yeah, I'm going to need more than that. And then if it says I need more than that, it'll retry the query over TCP. And if it retries over TCP, then it can get a whopping 64K response, which is generally enough to carry just about anything. Yeah?
I have a related question. Does that mean like the response size should be fixed because every time it will fetch either IPv4 or IPv6 address for the respective query, right? So how does it will vary in the length?
Well, that's a good question. So the question is, Why would the length vary? If you're just looking up IPv4 or IPv6 addresses, IPv4 addresses are 32 bits long, IPv6 addresses are 128 bits long. You should know how long that is, right? Well, there's all kinds of other stuff. Remember all those sections in the DNS message, the authority section, the additional data section, all those things. Those also carry resource records. Sometimes they're the records that tell you the authoritative name servers for the zone. The number of those will depend on how many name servers there are that are authoritative for the zone. They'll also depend on how long the names of the name servers for the zone are. So that's variable. There's something called DNSSEC, DNS security extensions, which adds cryptographic security to DNS. And so then you get records that are effectively digital signatures covering records in the answer. And those are enormous because they contain digital signatures. So a lot of that stuff contributes to the variability. You can very easily get up into the range of a couple thousand bytes in a response. Yeah?
The query from a resolver to the local DNS is always UDP.
Is what?
Always uses UDP.
The query from a resolver to a local DNS server almost always uses UDP by default. Yeah. There have been resolvers that by default use TCP. There was one in an old version of IBM AIX. But unless you're running IBM AIX like 3.2, you will not see that behavior. Yeah. I don't know why it did that, but it did. Any other questions? Yeah.
Caching, will the domain name also be cached or just the top level?
I'm sorry, will the domain name be cached or?
Yeah. Will the domain name like www.infoblogs.com, will that also be cached or just the top level?
Oh yeah, anything that we talked about that's returned in a response can be cached. So the address record for www.infoblogs.com, the names of the name servers for com or infoblogs.com, any of that stuff can be cached. You can even cache negative responses. If a name server tells you there is no IP address for www.infoblogs.com, you can cache that. So the next time somebody asks you, you don't have to go look again.
What if it pops up again?
If it pops up again, the negatively cached response also has a time to live. So eventually that will be discarded from the cache.
The developer can cancel the time to live if his popping up is faster than what he expects.
No, you can't do anything to, for example, remove your cache data from caches around the internet. There are millions of recursive name servers out there that might have something cached, and there is no mechanism within DNS to say.
He could ping all his IP address stored points, right? Like he could have, when his server was down, so he could actually probably try having a log of who are requested to servers when his server was down.
Yeah, that's an interesting hypothetical, but in practice that does not happen. I mean, for example, if you're actually operating name servers out on the internet today, then a lot of the queries that you get are coming through a NATed IP address, right? So all of these individual IP addresses are being translated into one IP address that looks like the one that's querying you. So you really can't track who queried you. There's no way to reach back to them because they're in back of NAT, right? So, and there's no signaling mechanism to tell recursive name servers that something has expired or should expire from their cache. You just have to set that time to live to something that you think of as reasonable. You as the administrator of a zone can set the time to live on every record within the zone. Yeah.
If I was admin for .eu of this portal, I could say I'm going to put this down for 3 days.
Yeah, you could say, I only want this to be cached for 10 minutes, or you could say, I want this to be cached for a day at a time. Yeah, it's totally up to you.
So during the cache time, probably say you have the most important pages, frequently accessed pages only cached, and I start working on the action page. Do I still having access to the data because it's already cached?
Yeah, I mean, generally speaking, if the system is fairly, if your web server, for example, is fairly stable and you're not moving it around, you can have the time to live on the name to address mapping for the server. You could have it be quite long if you wanted to. But remember that if some emergency arises and you do have to change its IP address, the time to live that you set will, if it's too long, that will encumber you. It'll hamstring you a little bit. Well, let's talk quickly about, go ahead.
Does the host need to know the IP address of the root server?
No, individual hosts running stub resolvers just need to know the IP addresses of the names of the recursive name servers that they query. It's the recursive name servers that have to know the names and addresses of the roots. Yeah. Well, let's take a quick look at something that happened just recently. How many of you guys know about the big attack against Dyn? Right, this was back on Friday, October 21st. Happened early in the morning. It was like 7 a.m. Eastern time. Well, let's take a quick look at that. Maybe through sort of the lens of your new understanding of DNS, this will be a little bit more interesting. So I've known Dyn for years and years and years. They're based up in Manchester, New Hampshire. They were founded out of the dorm room of Tom Daly and Jeremy Hitchcock when they were at Worcester Polytechnic. And they became a really big DNS hosting company. So that's what they do. They host zone data for other companies. You pay them, they run this widely geographically distributed infrastructure of very fast name servers at points of presence around the globe. And they run Anycast on all of them. They've got a ton of capacity. The idea is that by using their infrastructure to host your zone data, you can get your zone data very, very close to your customers. Right? Because these guys have a point of presence in Johannesburg, South Africa, and they have one in Sydney, and they have one in Singapore. Wherever you have customers, they've probably got a name server close to them. And if you're trying to do that yourself by setting up your own authoritative name servers close to those customers, that'd be a lot of infrastructure to maintain, right? And you got to negotiate some contract with a hosting facility in Johannesburg, South Africa yourself. That's a big old pain. So, on October 1st, Dyn's constellation of authoritative name servers was attacked. It was attacked by something called the Mirai botnet. The Mirai botnet consists primarily of IoT devices, Internet of Things devices, that come from a particular manufacturer, in fact, most of them. A lot of them are IP CCTV cameras, closed-circuit television cameras used for surveillance. Some of them are digital video recorders. I won't name the Chinese manufacturer that makes these for two reasons. One, because actually the Chinese manufacturer doesn't sell them directly, they OEM them, and so if you bought one of these things, you would have bought it from another company anyway. Also because in the wake of this particular attack, the Chinese Ministry of Justice has threatened to sue anyone who impugns the reputation of their crappy manufacturer, which gives a new meaning to the Ministry of Justice, somewhat Orwellian meaning. The Mirai botnet was previously used in an attack against a website called KrebsOnSecurity.com, run by a security pundit named Brian Krebs. Now that, up until the 21st, was the largest DDoS attack ever recorded. It peaked above 620 gigabits per second of traffic. And it used mostly garbage traffic, just hurled garbage traffic at Brian Krebs' website. Now I should say that this isn't Brian Krebs like running a website in his basement. His website was hosted by Akamai. And Akamai was doing this effectively as a courtesy to Brian because he's a good guy and Akamai's got a ton of bandwidth. And even Akamai, in the wake of this attack, said, yeah, you should go somewhere else. So the impact of this attack, it hurled a ton of traffic at Dyn's name servers. The estimate is that it hit 1.2 terabits per second, which is just about twice the largest recorded attack that we just saw on the previous slide. At this point, we don't know whether this traffic was junk traffic or whether it was legitimate DNS queries. And that's important because if it was junk traffic, then the attack is what we call a volumetric attack. It saturated the resources between Dyn's name servers and the internet. Right? It clogged the pipes, basically, between Dyn's name servers and the rest of the internet. If, on the other hand, it was an in-band attack that actually used DNS queries to overwhelm the Dyn name server's capacity to respond, that's a different thing. Right? The latter, an in-band attack using DNS queries, we might have been able to resist that. We might have been able to survive that. If somebody just clogs your pipes, you're done. Right? There's almost nothing you can do. You've got to redirect that traffic to a big scrubbing center operated by a commercial provider like Akamai or another commercial provider called Arbor Networks, and they can go through it and groom that traffic and send you the clean stuff. Regardless of which kind of attack it was, the name servers were rendered unresponsive. There were 3 different waves of attacks. Because you couldn't get answers from their name servers, there were all kinds of web properties that were hosted on those name servers that you couldn't get to. It's kind of a laundry list of people on the internet. So Netflix, what else? PayPal, you couldn't pay with PayPal. There are a couple of cloud-based single sign-on providers, Centrify and Okta. Spotify, so you couldn't get your Spotify tunes, just, right, a big, big, big deal. It seemed effectively like on Friday the internet was down. And it even had some collateral effects. So for example, my company, Infoblox, we use Okta as our single sign-on provider. So because we use Okta, we couldn't get to Salesforce. Even though Salesforce wasn't DDoSed, we couldn't log in because the Okta servers couldn't communicate.
And campus at the same issue for DDoS.
Yeah, okay, yeah. So you guys know exactly what happened. So how exactly did this happen? Well, the Mirai botnet, believe it or not, is supposed to have 1.5 million Internet of Things devices in it. And the reason that it's so easy to get these devices in this botnet is because this particular Chinese manufacturer, whose name I won't mention, they ship all of these devices with the same default password. What's worse, not only are these things shipped with the same default password, they have a web-based graphical user interface that you use to configure these CCTVs or DVRs or whatever, and you can change the password that you use in the graphical user interface. But that does not change the password that you use to access the device via SSH or, believe it or not, Telnet. You cannot change that password. Right? So all of these things out there, easy to compromise. The source code to Mirai was actually released publicly in early October. The person who apparently developed the malware that infects these devices goes by Anna Senpai, and Anna Senpai said, "Here you go, world. Here's the source code. Anybody who can code could actually grab a copy of this. It's actually available on GitHub if you want to go look for it. Anybody could grab a copy of this and gain control of this botnet." I'm not suggesting this, but it is possible. So what that means is this botnet is still out there. It is still out there. According to whoever Anna Senpai is, at any one time you do a poll, you can get about 300,000 devices in the botnet to answer the call, and then you can launch a mammoth DDoS attack against somebody. There's a reason, actually, that these devices are so useful, not just the fact that the security, the out-of-the-box security is so lousy, but because these devices have to have high bandwidth connections to the internet. Right? They're CCTV devices. They're effectively streaming video over the internet to somebody who's doing remote surveillance for some company. Right? Or they're a DVR, in which case they're also streaming video. So the manufacturer said you got to have like 10 megabits per second or higher connection to these things if you're going to deploy them. Moreover, they have to be accessible from the internet. They can't be hidden behind a firewall like my Nest thermostat is, which would be difficult for folks to compromise because it doesn't have an internet routable IP address. These things have to because they have to be remotely accessible. So this is a big deal. This is a really, really big problem because these IoT devices are coming out in waves and waves. We're seeing tremendous proliferation of these devices on the internet. They're cheap, they're poorly designed, they have very poor out-of-the-box security, right? Because they're so inexpensive in many cases, the manufacturers don't have the opportunity to amortize the cost of doing good security work across these things. Unlike, for example, your laptop, which cost $1,000 or more, right? Somebody had to pay attention to the security in that device. So we've been talking to lots of folks out there about this. One of the simplest things you can do to combat attacks like this is just to diversify your external authoritative name servers. Those authoritative name servers that advertise your data to the outside world, don't go all in with one provider like Dyn. Right? I like the guys at Dyn. I want to see them succeed. But the problem is if you rely entirely upon Dyn for your external authoritative name servers and they get attacked or one of their other customers gets attacked, you will end up collateral damage. Because that botnet is lying out there waiting to be trained on another target. In fact, it was implicated in the recent attack against Liberia. Did you guys know that Liberia was offline? No. Anybody accessing Liberian websites? No, I guess not. So just by diversifying a little bit, you could either use some of your own authoritative name servers and augment those with a provider like Dyn, right? You could use, what we've been telling people is use some Infoblox name servers and use Dyn, or use a couple of DNS hosting providers. Use Dyn and one of their competitors like VeriSign or whatever. Right. Still, if you in particular are targeted, right, if you are the organization that's targeted with a botnet that large out there on the internet, if that thing is trained on your set of authoritative name servers, you will probably go down. But at least, if you are not the target, and if some other company or the hosting provider themselves are targeted, you won't end up off the air. All right. Any questions about that? Yeah, go ahead. Are there any other attacks involving DNS besides DDoS attacks? Oh yeah, absolutely. There are things called cache poisoning attacks, where somebody works to inject bogus data into the cache of a recursive name server. There are attacks that use DNS as a tunneling mechanism to get data out of the inside of a protected network through DNS out to the internet, or to infiltrate data from the internet into the network using DNS. There are lots and lots of things. Yeah, unfortunately. Any other questions? Yeah.
How does the reverse lookup work?
How do reverse lookups work? Well, that's a good question. So yeah, it's a good question, because if you think about it, the way that you map from a name, given a name, to an IP address is sort of straightforward, right? We navigate the namespace in the way that we saw. We find the zone that contains the answer. We find the authoritative name servers for the zone that contains the answer. We get the answer. But if you're given an IP address, how do you go backwards? And the answer is you build a parallel portion of the namespace where the labels of the nodes are the octets of an IP address. So there's another part of that namespace that we showed, which was over here on the right, so I'm still waving at it, that's called the in-adder.arpa domain. And below that, the first level below in-adder.arpa, it branches 256 ways to labels that are 0 through 255. Right? And each one of those branches 256 ways, and so on, down to the fourth level. And so if you look down there, if you follow that down, create effectively a domain name out of the octets of an IPv4 address, then you'll find attached to that a record that points back to the name. But it unfortunately has to be managed completely separately from the forward mapping, and a lot of people don't do that. Yeah?
So, as the university has its own server of data, we, using the private security thing, like you said, they are managing some other companies' data in a server, which was attacked, right? Right when they saw a surge in queries, which you said happened in 3 waves, they could have shut down their servers, right?
Well, they could have shut down their servers, but if they'd shut down their servers, that would have been the same net effect as the DDoS attack, right? No one would have.
Because they know someone is attacking, they could kind of set up a firewall or stop the queries coming from certain kind of device or something like that.
Well, but you don't. I mean, given a given source IP address, how can you tell what type of device that is? Right? You don't know. If I just read out an IP address, you wouldn't know what kind of device that was. Right? None of that stuff. None of those things are actually practical. And in a volumetric attack, even if you had a way to filter it out, on a particular firewall, the pipe to the firewall would be saturated, and you wouldn't be able to get anything through it. So it doesn't matter.
The firewall can drop the answer, but the whole point of the DNS is to service.
Right. I mean, if they come in and they're actually legitimate DNS queries, you can't drop them because you can't differentiate between the legitimate queries and the ones that are being generated as part of the DDoS attack.
So VR is kind of an open vulnerability, right? How to address such vulnerability? Like how to address such kind of problem when we know that this is a problem?
Well, it's a very difficult problem, and there's no easy solution. I mean, the easiest solution in this particular case is just to have a diverse set of external authoritative name servers. But as to the general problem of the susceptibility of name servers or any internet resources to DDoS attacks, hey, if you got a good idea, then start a company.
Do they not have any DDoS scrubbers?
They apparently Dyn did have some DDoS scrubbing capabilities, but not enough. Yeah, not enough to resist that particular attack. Yeah, 1.2 terabits per second is a lot. Yeah, that is an awful lot. Okay, any last questions? All right, well, thank you all very, very much for your attention. I appreciate it. Thanks.